we have a system of pulleys. We have one side of the system. Let's say we are using the system of pulleys and the rope to lift some weight, 600 newtons, and we are analyzing this machine. So the problem statement, if you want to write it, let's put it this way: determine the tension in cables and also the force P required to support the 600 newtons force using the, specifically is mentioned that these pulleys are frictionless, so don't need to be worried about the friction there. Using the frictionless pulleys pulley system, I guess. Pulley system. All right. So we have a machine, right? You can look at the system of pulleys as a machine. We have 3 pulleys in this case. They're all connected together with one rope. Pretty much, the rope is attached. It starts from here, attached to the center point of pulley A, goes this way. It goes around pulley B, and then goes around pulley A, goes up, goes around pulley C, and here we are applying force P. Right, that's pretty much the path for this rope, if you want to follow that. All right, so what I'll do is that, well, I'm asked to find force P and also find the other forces, pretty much all the internal forces. Let's see what we can do. All right, we can start with the whole system if you want. We can draw the free body diagram for the whole system. I isolate this whole, let's say, machine right there, like this. And then the only forces, there's going to be an external force right here, 600 newtons, and we're going to have one force there, which is a support force. I can just call it R. And the force that, that cable, I would say, the force in that cable that the whole system is hanging from. And we have force P. We don't really get that much out of this, because if we write the summation of forces in y direction, we just get P plus 600 is equal to R. So drawing the free body diagram of the whole system is not going to give us, it's going to give us an extra equation. We'll see if we need it, but we cannot immediately find the reaction force, I would say, support force. So let's just go with one by one. Let's take a look at each part of this system. Right? And what I'm going to do is that I'm going to draw the free body diagram and write the equations of equilibrium for pulley C. Then I'm going to draw the free body diagram and write the equation of equilibrium for pulley B. And I do the same thing for pulley A. Let's see what we get out of these and writing these equations, if we can find all the unknowns that we want. So let's just start with pulley C. All right, so free body diagram of that. Let me attempt to draw the free body diagram. Let's say this is the pulley right there. This is the biggest pulley. So what forces do we have? We are looking at this free body diagram, right? And this free body diagram right here. Or we are isolating this. And we're looking at the free body diagram for pulley C. We have P as force right there. It's force that we're applying supposedly to lift that 600 Newton weight. We have, well, let's see what we're cutting in this line. Right? We're cutting this here. We're cutting the rope again here, and we're cutting this rope there that is holding the whole system. Tension going off from point C. Exactly. That we have to take into account. Another equal P on the other side. Yes. So we're going to have another P on the other side. Exactly. So this would be the one from this rope right there. Right? And I'm going to call that, let's just call it R as a reaction support or support reaction. Then we have another force, right? We're cutting the cable on this side too. Oops. We're cutting the cable on this side too. So we have to take that into account, as Richard said. So I'll put it here. Now, what is the value for that force? Can someone tell me that? And Richard says it's P. Is it correct? Does anyone have any different opinion? All right, so that is correct, because we said, remember, when we're talking about ropes and chains and threads, we said whenever we're analyzing those, remember, the force throughout the cable is the same. So if you're applying force P on this side, on the left side, the force within this cable should still be P on the other side, right? Because it's the same cable. What else we have there? We're also cutting through this line, right here, this connection between pulley C and pulley B. So we have to take into account the force between them, right? That would be an internal force. Direction, most probably it's going to be tension. So I'm going to put it in this way because it's holding everything. So let's call this, to follow my own notation, let's call this T. Right? So this is pretty much the free body diagram. I have the force P on that side, the rope on the other side. Throughout the rope, the force is constant, so another P on the other side of the pulley. R is the force I put there because I got rid of the connection between pulley C and the ceiling in this case, let's say. And T is the internal force between C and B. I'm isolating pulley C, so that should be taken into account. So there is only one direction in this case. Summation of forces in y direction should be 0, and I'll take upward as positive. So that will give me minus P minus P minus T plus R, I guess, is equal to 0. You can write it in a, I guess, I don't know if it makes it better. R minus T minus 2P is equal to 0. All right, I got one equation here. And still, I don't really have, it just gives me some relationship between these forces. That didn't really help a lot. I cannot find any of these forces by just knowing these, this relationship. I don't know P, I don't know R, and I don't know T. So I need more equations. I have 3 unknowns, and I only have 1 equation. So I need more equations. So keep going. Let's take a look at pulley B. Right. This pulley right there. I'm isolating this now. Let me draw it here. Pulley B. All right. I'll put an attempt to draw it. Let's draw it right there. All right. Let's look at the forces on this. Well, there is one force between B and C that I call it, which I call that force T. And let's just put it right here before we go further in the opposite direction. Right? This is the interaction between pulley B and pulley C. So I flip it and put it on pulley B. Right? They're equal in terms of their magnitude. The direction should be the opposite. All right, so what else? I'm cutting and isolating pulley B. Going through, well, this is a little, we also have 2P. Exactly. We have two ropes. So this is a little mid-right. This is the isolation line. Right? That rope is not included. So they're going to be 2p again. We're cutting the ropes again twice. And we said the force throughout the rope is the same. So all I need to do is just I have to put 2p's downward here. Right? This is going to be p and this is going to be p. And that's pretty much it. Well, there is nothing else. If you look at that pulley, I pretty much took into account every possible forces or every force applied to that. Two sides of one rope I had there, and I had the connection between B and C, which I took that into account. So summation of forces in y direction is 0. Again, we only have one direction, so we just write the equation in y direction. In x, doesn't give us anything. Moment, we are not given the radius radius for, let's say, pulley B or C or A. So pretty much that's all we got. That would be T minus 2p is equal to 0. Another equation we got. All right. Still, this is good. We have another relationship between T and P, but we still do not know P and we do not know T. So we cannot use this. We cannot find anything out of this. So going to next pulley. All right, this one. Now I'm isolating this one. Let's put it here, if I can fit it here. Pulley A. Right. And let me draw that pulley here. None of these actually are the right proportion, but all right. So I have 600 downward. I can just, it's pretty much, if you follow the line of action for this force, it goes all the way to the center. So I'll just pretty much put it right here, downward, apply to the center. That's something that I know. This is 600 newtons. P is equal to 200. It'll be 3 P's. Exactly. Yeah, Connor. And Richard, you pretty much got the final answer, but that's correct. Let's go step by step. So we have, as Connor said, we have 3 P's. We are cutting the rope 3 times. So obviously, we're going to have 1 P here. That's the force in the rope. Another one there. And also another one right here. Right? Keep in mind that this is the rope. Right? These are all the ropes. This is the rope, this is the rope, and this is the rope. And they're part of the same rope that force P is applied to it at one end. So the force has to be the same throughout the rope. Right? P, P, and P. So summation of forces in y direction should be 0. That'll give me 3P minus 600 is equal to 0. So P becomes 200 newtons, as Richard said. Right? That's force P. I was asked to find the force P required to support this. Now, once I know P, right, this is, let's say, the third equation. I know P, I can go back, use equation number 2 to find T, and then use equation number 1 to find R. Right? Pretty straightforward, hopefully. From, let me just put it here, from 2, or maybe to separate it so later on you guys look at it, things are not confusing. There you go. So from 2, we get T. T is 2P, which means it's 400 newtons. And once I know T and P, I can go to equation 1. So it's going to be 400 plus 400. It's going to be 800. From equation 3, R becomes 800 newtons. R and T.